All right, we are Team Euterpe, and this is our final design review for our capstone project, AsparaBot. So to give a quick overview of what we'll be touching on in this presentation, first I'll go over the project definition and overview, then we'll go over chassis and testing environment, then Gantry, Actuator, Drivetrain, Asparagus identification, navigation, system electronics, design outcome versus requirements, and finally we'll be discussing our results and what we've learned, and then our conclusion. All right, so to go over kind of why we started this project. So the US agricultural industry is facing a severe labor shortage, partially due to COVID, partially just because of trending job market patterns. And asparagus in particular has been hit hard because there's a very small window of growth. It's actually only about 1 day that you can harvest in between. It requires skilled and intensive labor. And for that reason, asparagus prices are continuing to climb and the supply could eventually start to decrease. So a lot of larger companies have attempted to combat this by moving farms overseas where labor is a bit cheaper and in higher supply, and sponsoring foreign seasonal workers to come work on their US farms. However, this is not really an option for these smaller farms because they don't have the money or the resources to, lobby with politicians, be able to bring in visa workers, be able to even move their farms overseas, stuff like that. And asparagus farms are really at a disadvantage here because actually 75% of asparagus farms are under 1 acre, so qualify as small scale farms, which is why we developed the AsparaBot to kind of cover that gap in the market. So this leaves us with a possible market of about $62 million worth of product. So yeah, our product does draw from a lot of already developed harvester bots. However, we are more targeted towards smaller scale farms in that, shorter battery life, much less expensive, a little bit more maneuverability, smaller size in general. So like smaller storage containers, stuff like that. Everything that kind of doesn't compromise the actual quality of the bot, but does cater more towards these smaller farms. So some questions we asked ourselves why we were doing this and what we plan to do with this are the following. So why is the problem of harvesting important? Why do these problems exist? Why are there labor shortages? And why are asparagus harvesting robots too expensive for local farmers to operate? Why is the US asparagus market declining? And why do local farmers not want to invest in one vegetables technology? And finally, why is the European asparagus industry growing so fast in comparison to the US? So asking ourselves these questions led us to the conclusion that we want to prioritize, in order to combat this, we want to prioritize making these robots cheaper, easier to use, and more suitable for small farms in like size and storage capacity, power capacity, stuff like that. And eventually we hope to make it more applicable to other vegetables as well. All right, so just to go over quickly what we've been doing these past 2 quarters. So one component is we've been working on the actual product design. So our product, as we've designed it currently, will include a robust drivetrain system, computer vision and LiDAR sensors, as well as like programming to back that up and use it for asparagus detection, a gantry system and storage, a gripper cutter mechanism, rechargeable batteries, a more robust chassis to protect from environmental factors, which our prototype doesn't necessarily have to have. The second component is our prototype, as I've kind of hinted to. So the prototype has already been designed and mostly manufactured. It's going to test the gantry and actuator systems, as well as the computer vision asparagus detection system. So just to go over, you might have noticed some things are missing. I'll kind of explain briefly why. So the drivetrain system is definitely more less untreaded territory. There's a lot of research in the market explaining how to implement a drivetrain system, and it's much less likely a point of failure. It's nothing new. So we will not be testing that for the prototype. Also for the LiDAR sensors, unfortunately, our LiDAR sensors have not arrived, so we will not be implementing that. Instead, we will be using the camera. But yeah, that's our project overview. Thank you.
Hi guys, I'm going to talk a little bit about the updates on our chassis product. And so the way it looks right now is the picture on the left. Kind of to review what we're looking for when we're designing the chassis product is we are trying to fulfill the given specifications that are that 1 acre on average holds around 1,600 asparagus. And each row is 1 foot wide. That would be like the row that contains the asparagus. And it's separated by 2 feet. So within each row or between each row of asparagus, you have kind of a walkway and it's 2 feet wide. Mature asparagus is around 6 to 12 inches tall. And those are the ones that we're trying to harvest. And each asparagus weighs around 300 grams. And so given those specifications, our design satisfies all of it because 1 acre on average holds 1,600 asparagus. We want to minimize the amount of intervention from farmers as much as possible. And so with the size of these baskets, it can carry 400 to 500 asparagus. So within 1 acre farm of like maximum density of asparagus, our AsparaBot can cover a quarter of that acre without any intervention. And then if it's a full acre, then the farmers have to come in and kind of intervene and clean it out so that it can be used further. Each row is 1 foot wide, separated by 2 feet. So as you can see, the area that the asparagus would pass through has in exactly a 12-inch clearance, so that in that clearance there's nothing jutting out. The asparagus that are too tall or not tall enough doesn't run into anything, get damaged. The asparagus rows being separated by 2 feet means that the distance from those baskets and wheels, since they're so low, obviously asparagus it doesn't have enough clearance for asparagus, so it needs to be under 2 feet, and that's 15 inches. 17-inch height satisfies the fact that mature asparagus are 6 to 12 inches tall. So again, we need to provide vertical clearance for our gantry system at its maximum height that it can clear all of these mature asparagus. And in this case, at maximum height, the gantry allows 17 inches of vertical clearance, which is good. And yeah, so kind of to talk about the sensor that you see here, our sensor system is going to be in the front of our chassis. It will be, you can hear more about it from the sensing and identification system, but there will be 4 of them to account for stopping distance. And it's going to be towards the front so that once it senses the asparagus, sequentially the asparagus will fall into the range of the gantry retrieval system, and then that would be the most convenient sequence of events. As for the kind of logistics of how the chassis will be assembled, it was kind of a big point to make this clear, so and make it accessible for people to actually build it. I'm not going to read through every single step, but basically it starts out with the basic frame. Once the basic frame has been assembled, we attach the gantry, and then very generically, then the drivetrain system. The drivetrain system would include the motor and the gearbox. There are holes in place to allow the electronics to connect to those from the battery to the motor and gearbox, and out of it we'll have to kind of pull out of also allotted holes the timing belts, which will be then connected to a sort of tensioning system, and we'll describe this more in the drivetrain system, and then it'll be connected to the wheels. And then finally, we attach all the external equipment such as the baskets and the outside casing, and the outside casing kind of serves to provide shade and protection from dust and dirt, so that, you know, we have a longer lifetime for our chassis. That is it. Thank you.
All right, so just a quick recap of the prototype component of the chassis. So the chassis build is completely finished. The gantry and testing board integration has been completed. We're redesigning the camera mount to hold the phone camera, which is just a minor thing that should be done pretty soon as well. And finally, the QR codes have been implemented. So yeah, here you can see on the left, we have first, on the furthermost left corner, we have the fully integrated testing environment as well as Gantry. And on the right, we have just the chassis itself. Yeah.
Hi guys, so I'm going to be talking really quick about our testing environment subsystem. And so what this refers to is basically the means as to how we should test that our mechanisms and subsystems actually work on asparagus. We can't actually go to a farm, so we have to mimic this somehow to the best of our ability so it's accurate. And so the specs, again, to start out with the specs, the rows of asparagus are 12 inches wide, 4 feet apart. So 2 feet of distance after each row. Mature asparagus are above 7 inches and they're spaced at least 3 inches apart. So there's your density spec. And we need to test for situations of various conditions, mainly the fact that there are different combinations of tall and short asparagus, different densities, and how that combination can cover our sensors in detecting the correct height and location. So there are a variety of arrangements, such as, mature asparagus are right next to each other, so high density. Mature asparagus are slightly spaced apart, lower density. What if there's a short asparagus in front of a mature asparagus? Will the sensors accidentally detect the short one? And will our gantry system still be able to accurately maneuver around the short asparagus, by satisfying our density specifications? And also things like lighting and stopping distance, and the fact that asparagus might be slightly tilted. And so a way to keep organized of all these things that we need to test is by writing up a testing procedure document that I can briefly go over. So basically we have a lot of subsystems. All of them need to work and also all of them need to integrate together. And so I made a doc for the procedure for testing so that once it works, we can get right into affirming that everything works together well. It's kind of just like a lab procedure document. So for example, for sensor testing, there's like a set arrangement of boundary conditions that we want to double check. So what happens if there's tall before tall, tall before short, three close to each other, or it's like offset by a small distance. So kind of again examining that density specification. So it goes from sensor to actuator to gantry testing, and then gantry with actuator, and then full sensing and retrieval test. And a lot of these tests are left for the product because we actually don't have, we don't have a drivetrain system. And I think we're currently waiting on the sensing to show up. But as we go along, as you can see, some of it is filled out as we go along and get the mechanisms to work. We're very much in our final testing and integration phase in the next week. So we hope to fill this out as everything becomes integrated naturally. And so, yeah, kind of to run through what the physical aspect of the testing environment is for a prototype. On the left, you see our chassis system. On the bottom is a sliding gantry that's connected to a rail of 2020 extrusion, aluminum extrusion, and on it is we screwed on a wooden board that would contain the platform for our styrofoam. And the way we initially intended on mounting the asparagus, because the styrofoam mimics the dirt, is that we wanted to stick a skewer onto the bottom of the asparagus and put the asparagus into, kind of stab it into the foam, but that wasn't very sturdy. And so alternatively, instead, we're kind of pre-drilling holes that the asparagus can be placed, and then using skewers to kind of mount and root that in underneath the foam. And so to kind of show the sturdiness of that, I recorded a video. And so the asparagus is a little flimsy because it's old, but the main point to note here is that while it's being hit towards the root and while it's trying to be while I'm trying to pull it up, it's not easily uprooted and it's not easily able to kind of move around in the base. And that is the physical aspect And also additionally, after all these assemblies are completed, we can kind of tell how high the asparagus can sit, and that's really important for our CV and sensing systems because they need accurate height so that they can accurately pinpoint the X and Y coordinates for a gantry system. And so we will talk about exactly how we came to this in other subsystems, but here's some quick previews of some of the testing we did with the testing environment, just to make sure that it works with our mechanisms. So this is our cutting mechanism. This just makes sure that the cutting doesn't accidentally uproot the asparagus and that it's firm. And part of the reason why these videos we're taking is because it's part of our procedures that we wrote up, especially in the initial phasing testing phase. We need to record and document clearly how these mechanisms work. And then additionally, this is a quick preview of how the gripper testing mechanism works. So yeah, just like documentation is mostly what involves the testing environment for both product and prototype. Thank you very much.
Okay, moving on to the gantry subsystem as a progress overview for this quarter. For the prototype, we finalized our design selection. We've chosen to use a Y-axis belt-driven system because it's inexpensive and experiencing relatively light loads. And since it's a prototype, we can adjust the lengths if needed very easily. For the Z-axis, we've chosen an off-the-shelf ball screw linear actuator. This was selected simply to make our design and prototyping process a little bit easier. So the prototype is currently under development right now. See some more pictures of the progress to that in a few later slides. As far as the product goes, we've chosen a belt-driven X and Y axis for the similar reasons as outlined above, but for the Z axis, ideally we would choose a lead screw driven linear actuator, which is non-back drivable in case of power failure. Some design justification we went through for the Z-axis linear actuator, simulating some transverse loading in order to test to see what level of forces experienced would cause failure of this Z-axis gantry mount. And we note that failure occurs at 8-pound force applied at the tip of the Z-axis. And just to verify these results, we did do some empirical testing where we loaded the sliding gantry with some weights and in order to test the loading capacity. And we expect about 4-pound force of force to be not enough to cause failing. And for reference, the actuator subsystem is less than 2 pounds. And just as a contingency plan, if we discover that this is still insufficient, we're going to add an additional rail just for the prototype, but for the product, we're already going to add this additional rail shown here. So this is the current CAD of the product gantry. You can see we've added this Z-axis translation using a dual shaft stepper motor. For the motor selection here, we're going with closed loop control as opposed to the open loop control that we're doing for the prototype, because we've determined that the added benefit of faster harvesting and higher precision is justified by the additional $1,000 or so that it would cost, because this amount is still well within our budget. We've determined that having that homing procedure for open loop control would accumulate a couple of minutes per row, which could add up to an hour or more over an entire acre, which we felt was very undesirable for our design requirements. As far as prototype progress goes, we can see that we've got a functioning Y and Z axis moving separately on the left and right videos here. And we can also see that we've begun to integrate into the chassis and testing environment. And next steps for us would be full integration of all electronics and mounting of the actuator subsystem. So just to look at some CAD of how that would work, the actuator attaches to this long acrylic plate with these 4 holes right here. And we'll simply rest below the sliding gantry. And this will slide downwards to harvest asparagus, where the green plane represents the maximum height that asparagus could be at. So you can see that it perfectly clears the possible level of asparagus and is able to have enough range of motion to cut asparagus at the base.
I'll now walk through our prototype CAD. So starting with the gripper, which is at the top, we have the motor which drives the rotary, and this in turn turns the mechanism which will drive the opening and closing of the gripper. The rotary is acrylic, and the remaining parts are 3D printed, and the axes are metal. The gripper uses a sliding mechanism which has plastic bearings which sit in a C-channel slot. And below we have the cutter, which also is a single motor, and it drives this blade here to swing towards the 3D printed blunt blade. And this blunt blade is retained by a bent metal rod held in place with this shaft collar. And overall, the way that this integrates with the entire system is that this area will be the point of mounting between the gantry, which will move this entire actuator up and down, left and right, in order to position the actuator around an asparagus, after which it will close around the asparagus, cut the spear, bring the spear to its final location, release the asparagus, and reset for the next cut.
So now that we have a CAD model finalized, it was important for us to understand grip and cut force in order to size our motors properly. So this involved a gripper and cutter force analysis. All of the data that we got for this analysis was provided by the paper listed above. So for the gripper, our guiding question was to find the maximum force to grip the most fragile asparagus without crushing it. And for the cutter analysis, our goal was to find the minimum force required to cut the strongest asparagus. After doing the calculations provided below, we were able to get that the maximum force before crushing would be 19.6 newtons from the gripper, and the minimum force for cutting should be 6.2 newtons. However, we don't always want to be grabbing the asparagus to a point right before it's getting crushed. It's sufficient to grab it just so that it's counteracting the force of gravity. So it was extremely important for us to do this minimum grip force analysis to get that particular parameter. So after doing a free body diagram and following the parameters listed below, we were able to get that a range of normal force that we would be expecting to counteract the force of gravity would be roughly between 30-ounce force to 40-ounce force. Plugging all of these values into our finite element analysis for our gripper, we were able to see that there is deformation without yielding and a sufficient factor of safety for us to proceed with this design. So after this, we were able to complete a mechanism analysis to understand how the input torque from the motor would translate into an output force from our gripper. So we were able to simplify this to a simple crankshaft mechanism, and we are having a governing equation and a diagram as shown here. And then after doing the analysis, we were able to gather the following equations to guide our analysis, which we then plugged into MATLAB, the code being provided here. And the output of our MATLAB analysis is shown in the graph on the left-hand side, which shows that the unity is reached for link length, where R1 is equal to R2, which is ½ an inch. Along with this, we're able to see that our system can achieve mechanical advantage. So this provides all the data we need to size our motors. And with that, with all of that data, we were able to make prototype motor selections as provided here. For both the gripper and cutter motor, there are independent values.
The gripper foam we selected was ½ neoprene foam, rated at 7 psi to compress 25%. We specified the pressure rating and thickness based on the gripping area, mechanism force input, and desired compression. We pivoted from our choice rated at the minimum pressure due to geometry constraints to arrive at the final selection, whose functionality was verified through testing. We will now walk through the build and test timeline for the prototype. In the first session, we learned that the gripper arm assembly is a delicate process as the pieces are very small and require precise assembly. The printed blade cover concept produced moderate compression, and gluing would help with security. We also need to fix the through-hole alignment and decided to extend the cover over the tip for safety. Next, we assembled the gripper arms to the motor mount and rotary. Since we did not receive our C channels for the slider, we improvised by using extra 1-inch square rails. We tested electronics by running a simple standalone test of the servo motor, where we oscillated the servo through its range of motion. On day 3, we first tested the sliding action of one gripper arm while we handheld the assembly in place. The motion was mostly smooth, so we moved to mounting with fasteners. Here we found that the opening and closing motion was interrupted and not smooth. Note that the framing used was a temporary substitute since we did not have our C channels. After tuning the alignment of the slider and rotary axes, we produced smooth oscillation in our testing fixture.
So here's a video of our first test after assembling the actuator, which includes the gripper, which is held in a closed position with the foam attached, the new blade cover, the acrylic framing, and the 1-inch rails. So as you can see in this video, the single swinging blade was not sufficient to cut the asparagus fully. It just kind of moved the stalk to the side. So because of this, we experimented with adding another stationary blade, just held in place with pliers. And as you can see in this video, this succeeded in cutting the asparagus. And here's a close-up of that setup that we used. So unfortunately, we were not able to manufacture a hole through the steel blade to fix it to the actuator frame. So we 3D printed a blunt blade instead and retained it using a bend rod, as you can see in this picture here. And then we moved on to testing both the gripper and actuator motion, but we ran into some issues in this process. First, we found that we weren't able to power both servo motors using the Arduino, so we used a benchtop power supply instead. And then second, our 3D printed axle on our linkage broke, so we replaced it with a press-fit aluminum rod. And after these adjustments, we were able to finally have a successful first freestanding system test with both the gripper and actuator action in sequence. As you can see, the asparagus is gripped and then cut. So our testing gave us some really useful information to apply to our final product design. So first, we found that the retaining ring and linkage positioning, as well as the rotary and slider axis alignment, is very important for a working gripper. And then we also found that the swinging blade, single swinging blade, is not sufficient to cut the asparagus, but adding a blunt stationary one is. We found that the selected motors for both gripping and cutting were strong enough for our application. And we found that an external 5-volt power supply is required to power the servo motors, and that the gripping foam worked well for varying asparagus diameters. And some testing we still need to do is testing our now functioning actuator subsystem with the asparagus that's fixed in our testing environment setup, which will simulate asparagus that's actually growing from the ground. So here's our current final product CAD. Like the prototype, it uses a dual sort of slider crank mechanism to turn the rotation of the motor into linear movement using sliders and C channels. Also like the prototype, the gripper and the cutter use 2 separate motors. However, something that is different that is in the product is that we're using brushed DC motors instead of the servos that we used for easy prototyping. And these motors are mounted directly into this frame for our actuator, which is also then mounted to the gantry here using these holes. So something that is also different for our product is that we use a bevel gear and these curved linkages because of our space constraint due to asparagus density. And additionally, informed by our testing, we added a stationary blade here so that this asparagus can be successfully cut. And so we're still finalizing this product CAD, For example, we're planning to add some more mounting points to stabilize the motors, as well as adding some panels to prevent dirt and dust getting into the mechanism. And then also refining how different parts are fixed together, keeping in mind ease of manufacturing and assembly.
So for the drivetrain subsystem, it's kind of important to highlight how we ended up at our current design. So kind of to walk through the initial process of how we thought of mounting the drivetrain, how we designed it. Initially, we were thinking of putting simply very straightforward, like a wheel on one side of the chassis wall, and then on the other, it would be connected to a different, like a box that would contain the gearbox and motor that would be also mounted to the chassis wall. And so the problem with this is actually that this makes the gearbox and motor stick out way too much directly in the line, the horizontal line of the wheel. That's bad for our application because asparagus grows vertically and we need to clear that area. As said before from chassis, we need to clear a certain amount of area so that we can guarantee that we can travel down a row of asparagus that's 1 foot wide and can contain up to 12 inches of asparagus. And so instead, we went for the design where we shifted the motor and gearbox up onto the chassis wall vertically. And then the caveat is that we need to attach a timing belt to this, which is an added complication, but this is a quick intro of the setup and initial mindset of how we came to our current design, kind of a really simplistic drawing breakdown. And then Sruthi will talk about specifically our current model.
Susan provided a great overview of how our system looks mechanically, particularly for the driven wheels. But I'd like to take a step back and look at how our drivetrain works holistically. We're going with differential drive steering, where our front 2 wheels are driven by independent motors and our back 2 wheels are caster wheels or they're undriven. So with that in mind, let's go ahead and look at our first analysis that we did, which was to try and understand what motor torques we should be looking at. So in order to do that, we defined some vehicle design criteria. Particularly, we took that the mass on each drive wheel would be 75 pounds. And we took that the radius of the wheel and tire would be 6 inches. So with that in mind, we were then able to look at some calculations. These calculations were guided by this University of Florida source. And following through all of these particular calculations, we were able to get that the motor torque should be 30 pound-foot, and that was our guiding value. So taking that value, we then started looking at motors, and that allowed us to make the motor selection of this 100-watt motor from ATO. And with all of that in mind, we were able to shift into CAD, into SolidWorks, and finalize our product design. So this is an isolated view of our CAD model, of our drivetrain on CAD and SolidWorks. And as you can see here, we have both the wheel and the motor mounted towards the outside of the chassis, where this long bar is simulating the chassis wall in this scenario. And as you can see, as the wheel turns, the motor is also turning, and in particular, the motion is being translated through a timing belt, pulley, and belt system. Particularly, I'd also like to highlight that we included a spring tensioner. So we have 2 belts in our system, both of which are attached to this tensioner. And this tensioner will allow us to change the tension in each belt as required, as they loosen or as they tighten. So with that in mind, we then identified 2 critical subsystems that needed further analysis to verify that the design will be sufficient on the road. And the first is this motor holder system, and the second is this flange system, which holds on to the wheel. The first critical subsystem we needed to analyze in this drivetrain model was the mounts and the holder that carry the motor and the gearbox. It was critical for us to verify that these parts are able to withstand the force of gravity of the motor and the gearbox. So after doing the FEA with all of the parameters provided on the left-hand side, as I scroll down, we see here that our stress concentrations are at holes, particularly where we have connectors, which is expected. But more importantly, our minimum factor of safety is 28, which gives us credibility that this design will work in our environment. So the second system that we found critical was the flange. In particular, we wanted to make sure that the flange is able to withstand the force of gravity of 75-pound force of the entire subsystem, or sorry, the entire robot on this one particular wheel. So after we did this analysis, we saw that the stress provided that there is some sort of bending action occurring, which is again expected. But more importantly, our minimum factor of safety is 6.1, which gives us confidence that this design will work for our scenario. So that gives us an overview of our driven side of our drivetrain system. Along with that, we have two caster wheels in the back that allow for the differential drive. So this provides us, this part provided here is the part that we will be utilizing in particular for those rear wheels. They have a 450-pound force capacity per caster, which gives us confidence that it will work in our system.
The goal of the asparagus identification subsystem is to identify mature asparagus and then send the locations of those asparagus to our gantry for harvesting. Our initial design involved just a distance sensor to sense the distance to the top of any mature asparagus, which are asparagus above some 6-inch threshold. However, further analysis of our margin of error, as well as the potential for asparagus to bend, resulted in us determining that we need additional computer vision to reduce the error in the sense position by sensing the base instead of the top of the asparagus. So our setup combines both a distance sensor to determine which asparagus are mature and a camera to then determine the base of those asparagus. And here you can see the overall sensor function. We start by driving forward, and then whenever the distance sensors sense a mature asparagus, we match that location of asparagus with the closest base location returned by the computer vision. And then we send those to the gantry for harvesting. And we repeat this until no mature asparagus are sensed, and then we continue driving forward. For the distance sensor algorithm, we opted for something pretty simple, as the precision really comes from our computer vision. So we just use a moving average filter over the sensor readings, and then check whenever the sensor reading dips below a certain threshold underneath the maximum distance. This indicates that the sensor has started to overlap an asparagus, and so we just wait until that reading stabilizes, indicating that the sensor is directly overlapping the asparagus, and return that value. Otherwise, we just return a max value, signifying that the sensor has not yet sensed an asparagus. Our computer vision design utilizes an initial segmentation mask over asparagus, which is sent into a perspective transform and then a base detection step. Our initial segmentation mask combined both color segmentation and edge-based segmentation. However, as you can see from this demonstration, it obtained a lot of false positives, especially near the base of the asparagus here, which is where we wanted the precision. And so we determined that this segmentation algorithm was not good enough. So we ultimately decided to switch it out for a deep learning based segmentation utilizing MaskR CNN, which we fine-tuned on 75 custom annotated data set. Here you can see here the MaskR CNN mask for the asparagus, and you can see for the majority of them, they're far more precise than our previous method. After obtaining these masks, we then take a perspective transform from our original image here to this view where the ground plane is orthogonal to the line of sight. And then we use a distance transform to compute the width of each asparagus and then compute its base location. And so notably, this step here, the perspective transform, requires an initial calibration step in which we place Aruku markers precisely in the corners of the area serviced by the gantry, and then use the images of the initial and final perspective to compute the required perspective transform. This should be done in the factory before the robot is sent to the customer. And then once the perspective is computed, we can save it and no longer need these Aruku markers. Instead, we just reuse our perspective transform during operation. We also performed an initial verification of the precision of our algorithm on this test image. And so we can see there's 5 asparagus whose bases are visible. We took the computer vision estimated base locations and also took manual position measurements and recorded the error for each. You can see here 4 out of the 5 have an error less than 1/4 inch, which meets our threshold. And so we have an accuracy of 80%. Finally, we needed to add additional steps to handle occluded asparagus. Our initial way of doing this was just to let the distance sensor, which should be naturally in position to sense any occluded asparagus once earlier asparagus are harvested. However, we forgot to account for stopping distance, which would mean that once earlier asparagus are harvested, the distance sensor is out of position to sense any asparagus behind it. We came up with several solutions and ultimately decided on this one, which utilizes 4 distance sensors spaced out by a stopping distance each. This makes use of the fact that our density constraint on the asparagus means that there's a maximum of 4 asparagus that can be in a line per row. And so as the robot drives forward, each one of these will be sensed by one of our 4 distance sensors, even if they are initially occluded. And this design was ultimately the one that was both physically feasible with the particular distance sensors we're using, as well as cheapest in terms of the number of additional parts. So here's our final setup. We have our 4 distance sensors, which are sensing the distance to the tops of any mature asparagus, and our camera, which is determining the locations of the base of all of the asparagus. And so whenever these distance sensors sense an asparagus, we match the top position with the closest base position determined by the camera and send the coordinates to the gantry. And again, this is a layout of the algorithm. The steps I just described are performed for each distance sensor. And whenever all distance sensors return that there's no mature asparagus in view, we just continue driving forward until one of them does sense a mature asparagus, at which point we send the corresponding base locations to the gantry.
All right, so here we're going to discuss the AsparaBot navigation, the self-driving subsystem. So the initial sensing algorithm was a design involving 5 photoresistors in an array, a blue strap on the ground, and blue LEDs. Because what we're essentially trying to do is implement a line following algorithm. We decided that this was the best way in terms of the market that we're trying to catch as well, using a special propylene webbing strap, which is resistant to mold into the environment. That'll be laid down next to the rows. And the initial sensing was, as I said, these photoresistors, but upon testing, these yielded poor results. So instead we transitioned to a camera-based color detection algorithm, in which you can see on the bottom right-hand picture, we'll have this sort of platform with a camera beating directly down onto the ground, shielded on all 4 sides, because it's a square platform, by these brushes to keep the lighting to a consistent, regardless of whether it's sunny or cloudy outside, as well as with a white LED beating down. So this camera is going to be continuously recording and saving pictures, and we're going to take that 1080p picture and we're going to convert it to HSV in our OpenCV library. And this allows us to filter based off of the blue hue. So we're essentially isolating wherever we see blue in the picture, and we're setting everything else to black. And testing yielded much better results, as you'll see in the next slide. And additionally, in the FDR, there will be additional testing. So really quickly, just to show you guys, we have this code right here, which is our output picture on the left and our input picture on the right. And then if we change it, let's say to another picture, we'll have, let's go D5. And we run it again. And then what we have as output is right here. So as you'll see in the FDR more concise, but this is what the algorithm does. Wherever it's blue, it sets it to white. And we still have the 5 sensor readings, which now David will talk about in the next slide.
To verify our navigation subsystem, we opted to simulate the navigation in order to save development time. So here you can see our simulation. We're simulating differential drive kinematics as well as the sensor readings. In terms of the control of our robot, we chose PID control, and we're taking a basic moving average filter over the sensor readings. And then to determine our p-value, we offset the indices of our array of sensor readings such that the center of the array corresponds to an index of 0, and values to the left correspond to negative indices, while values to the right correspond to positive indices. And then we apply quadratic scaling to these indices. And our final p-value is the average of these scaled indices for just the readings that are positive. I and D terms are computed normally from this p-value, and our final PID combination corresponds to our desired angular velocity of the robot. And then we can use differential drive kinematics to then compute from the angular velocity and our desired top speed what the specific inputs to each wheels should be. To verify this control system, we are simulating 3 types of noise. And so you can see that here. So you can see we're simulating false positive noise in the background of the sensor and false negative noise of the sensor along the line, as well as the robot moves, you can see these kind of random shifts corresponding to actuation noise. With these noise, we can find the final noise tolerances for our control system. So we simulated 1,000 combinations of our 3 types of noise and repeated each combination 10 times. And from this, we can get the fraction of the time the line was successfully followed for each combination of noise, as well as the average error the robot picks up as it traverses the line. And you can see a plot of these combinations. So here is the plot of % of the time the robot successfully completes the line with our 3 combinations of noise. You can see it tolerates up to, at maximum, around 40% of the line covered in dirt, while only around 5% of the line covered, or 5% of the background covered in grass. And these are for 100% successful runs. So as you can see, our navigation control system is far more susceptible to false positive noise than false negative noise. However, this is still okay as our background is going to be mostly dirt. And so we are more concerned about the false negative noise rather than the false positive noise. In addition, you can see our actuation noise. We can tolerate up to almost an inch magnitude of kind of shifts in the robot as it traverses the line. And again, this is a reasonable number as we expect the farmland to be fairly flat and void of any large obstacles that could shift our robot as it moves. Furthermore, if physical testing shows that these noise tolerances are too low, we can add additional more advanced filtering onto our sensor outputs in order to reduce the noise. Finally, you can also see the average error of the robot for each of these noise combinations. And you can see here for a large majority of the successful runs, the error during straight sections, which is when we will be harvesting asparagus, is between 0.2 and 0.3 inches. And so that's a good sign as the impact of the control system on the harvesting and identification subsystems is going to be pretty minimal.
All right, so right now we'll talk about the electronics and power subsystem, which basically ties in all the electronic components. So to start off, the work that was done was to identify the requirements of this. So this means going through every subsystem in our AsparaBot and identifying those electronic components and putting them together in a list and figuring out how to tie them together. So the solution to that was a Raspberry Pi as our main processor, which brings everything together. We saw that this was enough to run, for example, the computer vision algorithm, because there's no training required. It just evaluates based off of the model that's loaded into it. And this is the most intensive task. So all the other tasks, which involve sending signals to motor drivers, those are all going to be a piece of cake for the Raspberry Pi. The actuator and the gantry subsystems, we added a layer of abstraction by adding an Arduino circuit and building an Arduino circuit with those subsystems and then making that connection to the Raspberry Pi. We did this to simplify wiring and connections. And lastly, our navigation, identification, and drivetrain subsystems are directly connected to the Raspberry Pi. This was also just for the ease of setting things up later, because these systems in particular are a more simple form of connectivity. And to power all of these components, we had to think between a battery and a generator, and we chose to go with a battery source because there's the rechargeability aspect and also the maintenance-free aspect that a generator or a motor-driven gasoline-powered generator would not give us. So we determined that we would need 4 batteries total, and the ones that we picked, the pictures in the bottom left, they're 12.8 volts each with 48 amp hours per battery. And since we're doing a series parallel config, we will have double the voltage and double the amp hour capacity. So we estimate that after a day of use, the batteries will obtain around 20% of their charge. And these calculations will be in the FDR. So really quickly, here's the higher level circuit that we have. The 2 things you should keep in mind is the red lines are symbolic of the power system, and the blue lines are symbolic of the integration with the Raspberry Pi for all the other electronic components. So as you can see, the battery bank, the power system, there's circuit lines leading to each individual subsystem. We also note that the gantry and the gripper the actuator are put in a dashed box as well. That's symbolic of the Arduino sub-circuit that we have there. And really quickly, also going over some power system calculations. These are all the power requirements for every single component that we have in our system. And these power requirements we were very generous with, because these are the max power that they'll take, which is entirely unrealistic because they're not all going to be running at 100% of the load simultaneously all the time. So to get like a worst possible case scenario, we got a total amp draw of 13.5 amp hours. We subtracted the actuator and the current because we know that when the drivetrain is running, the actuator and the gantry current is not running. So really the worst case scenario is just having the drivetrain running by itself. Upon subtracting that, we find that we have around 6.2 hours with fully charged batteries of runtime, which again, this is worst case scenario.
Up next is design outcomes versus requirements for our subsystems. So for identification, ideally we wanted to have 95% of mature asparagus detected. We ended up with 80%, which is less than what we wanted, but still solid. For asparagus locating error, we have figures better than minimum, which is good. Detection rate can be improved with increasing training data and time for the mass RCNN model. For navigation, our requirements were to have a robot follow a path through all rows of asparagus over 1 acre, travel at a top speed of 0.33 meters per second, and tolerate 4-foot turns. Those are diameter, by the way. We successfully made a PID controller that successfully follows lines with 4-foot diameter, turns with the top speed of 0.33 meters per second, tolerates up to 0.9-inch magnitude actuation noise, 40% false negative noise, and 5% false positive noise with 100% success rate in line following. Average error during straight sections when a robot will harvest for the above noise profiles is less than 0.24 of an inch. Our biggest change for the drivetrain is moving the motor and gearbox up on the chassis wall, which is necessary to clear the area under the chassis. For system electronics, our requirements for finding parts that would fit the specifications, our robot demands, we settled for Raspberry Pi for a CPU and a rechargeable battery or a generator for the power source. So our robot should minimize farmer involvement. Our robot should minimize farmer involvement, harvest as many asparagus as possible, and incorporate gantry, drivetrain sensor, electronics, and actuator systems. A robot will be able to cover 1/4 of an acre before needing to be emptied and provides the necessary clearance underneath for asparagus. For testing requirements, we need to account for the different situations and edge cases that may arise when harvesting, and we have done this through our testing procedure listed below. So our gantry should successfully traverse to the target location and be able to support expected loads, and through testing and simulation, we've done this successfully. Our gripper for the actuator should smoothly translate along the glide rails using a modified slider crank mechanism, successfully grip asparagus of different diameters securely and without crushing the stalk. The cutter should successfully clip the base of an asparagus stalk in one cut with stationary blade addition. We have to make sure that actuator total weight is within the load capacity of the gantry. We confirm that these requirements have been achieved through physical testing and simulation.
For conclusion and discussion, I'll be going over the main results and takeaways of our key subsystems. So for the gantry, from simulation and physical testing so far, the current setup is strong enough to withstand torque caused by vibrations, gantry movement, and asparagus cutting motion. But we do have a contingency plan of adding an extra rail if needed for real-world conditions. For the actuator, our current system successfully grips and cuts asparagus of varying diameters, but we will be working with the testing environment subsystem to ensure that it still operates correctly on asparagus when it is fixed with conditions similar to growing from the ground like on a farm. For asparagus identification, the testing outcomes are approaching our defined design requirements, but we have plans to improve these by increasing our training data. For navigation, our results from the simulation show that our line following system meets our design requirements. However, if real world testing shows differently, we can add filtering to reduce the noise we're currently seeing. For all the subsystems, we're making sure to consider and recreate and simulate real world conditions that AsparaBot might encounter on an asparagus farm, such as bumpy terrain, dirt particles, different asparagus growing configurations, etc. We realize how crucial this is to designing a robot that will be an effective solution for our defined problem space. Yes, thank you.
I've put my trust